Hello, I am Ryan and I am the subteam lead of AIDE Python. We work on the Agoclara infrastructure design engine, which writes code that calculates plant dimensions. And you can see more at this website. So, what do we do? Well, first, let's talk about what AIDE actually is. So, the Agoclara infrastructure design engine is a whole engine that all of Agoclara and everyone can use that allows people to create and design their own gravity-powered water treatment plants at any size. So what that means is that we start off with these three subteams. So we have AIDE Python, AIDE FutureScript, and AIDE Onshape. And what that means is that we first start off with AIDE Python, which we create code to calculate the design. So we use Python to make this object-oriented structure that actually separates all of the components of the plant into each different objects, but they all connect to make sure that the properties actually trickle down to all of the subcomponents. And we take all of that code and move it all to the AIDE FutureScript subteam, which calculates the designs that works closely with the AIDE Onshape team, which actually takes those designs and CADs it for people to visually see. Then we take the output of that into back to Python to actually generate plant design documentation for anyone to clearly read and understand what is going on in a water treatment plant. So let's move on to actually just AIDE Python. So as you can see here, we have an excerpt of some code here. And this is part of the Python section of our design code. So as you can see here, this is for the linear flow orifice meter. And as you can see, there's actually subclass component. And what that means is that each component of the plant is connected to this superclass component, which essentially means that you can now trickle data all the way down to all of our subcomponents. So as you can see, we have our design properties, such as head loss or safety factor, and if anything needs to come down from, say, the intrastake flocculator assembly, it all trickles down to the LFOM, making sure that everyone will keep the same design properties to make all the design properties uniform between the whole plant. Now, as you can see, on the other side, there's actually the final product of our LFOM, the CADed full version of our LFOM. And what this means is that we go through the whole tree that I talked about before, where we go from AIDE Python to AIDE FutureScript to AIDE Onshape, getting out our fully CADed version. Okay, so next I'll bring in Candela to talk about manifolds.
Alright, so we have created a generalized pipeline functionalities, and this pipeline functionality contains 4 classes. It contains the elbow class, the pipe class, the T class, and the manifold class. And all of these classes have different properties that are going to return information about pipelines. So the most recent class that we have added over the summer was the manifold class. And so right now, however, we are having issues. We're trying to figure out how to make the dimensions of the manifold the dimensions that they should be. So we are currently in the bug fixing stage of the filter assembly. So basically our goal this semester was to complete the assembly, and this was basically the last component that we had to implement. And the purpose of this filter assembly is to filter water through sand, and we basically followed Monroe's O-Stars design in doing so. But right now we've already finished the design code, but we're having issues trying to get the same output that Monroe's code does. Yeah. And now I'll take it over to Sneha.
This semester we completed the design code for the filter assembly. We took the filter from Monroe's collab notebook and then transformed it into this design. We transformed the design to include the new component structure that we actually worked on this past summer. With this filter assembly, there is a subcomponent called the filter box class. The filter box handles properties outside of the inlet pipes, and it's a central part of the O-Stars design. In the box, there are properties such as head loss, backwash velocity, etc. We implemented the filter box using default values. It's important because the filter box is used in the filter to ultimately create the filter design. The filter assembly is currently in the testing phase. These are actual code snippets from the design code of the filter assembly. On the left is the filter box class, and on the right is the filter class. These code snippets show how to initialize or create a filter box and filter. You can see the init functions define the different design inputs. Here is the documentation for the design code of the filter assembly. We document each property and each design input, and on the screen is just different examples of how we document. Now I'm gonna pass it off to Ryan.
Okay, so now I'll talk to you about what we're planning to do next semester for AIDE Python. So the first thing that we want to finish is actually integrating all the components in tandem. So as you can see, we have this tree, which actually shows our overall object formation of the water treatment plant for Agua Clara. So first, we start off with our head, which is our plant. Then we move down to the children of that, which is our entrance tank flocculator assembly, our filter, and our sedimenter. Then all of those have their own respective children showing the sub-components of the water treatment plant, such as the entrance tank, flocculator, filter box, so on and so forth. But as you can see in that corner over there is the CDC. And the problem is that when we actually implemented the CDC, we did not connect it to the overall plant structure. So that is something that we're going to plan to work on next semester to fully integrate it and to make sure that everything works in tandem. Next, we're building a plant documentation engine for delineating completed designs. So as you can see here, we first have our code snippet, which works on a flocculator. Then we can now serialize those properties of that flocculator into a whole JSON that allows us to actually connect it to this design template. And what this design template is that it's a whole structure which basically just reads out to the person what's happening in our flocculator, what's happening in any other component, but it has these brackets here that actually allows us to input the stuff from the JSON into our design to make sure that you get a whole readable PDF talking about what's going on in a water treatment plant, and these are the dimensions that you need to actually build your own. And this is really helpful for overall research, but this is also helpful for anyone that's actually constructing the water treatment plant down in Honduras, down in India, so on and so forth. So this is something that we really want to get to work on for the next semester of AIDE Python to become the whole documentation sub-team for Agua Clara. Now, we'll also be working on deploying the website for AIDE. So as you can see here, we have a snippet of our homepage, and as you can see, it says experimental there. And basically, what the whole point of this website is to talk about the design code that we work on for AIDE, but also working on the research side from Research IT. So here we have snippets to how to make your own plant component for your own water treatment plant, but also how to use each water treatment plant in ways that, say, NumPy documents all of their functions and all of their classes. So this is something that we really want to get to move on for all the research sub-teams that want to work on AIDE, but also anyone that's looking at AIDE to make sure that they have their own properties for their own water treatment plants in the future. And all of this together is the plans that we're going to be working on for the next semester. So here, I'll bring back Candela and Sneha. And you can just ask us questions or recommendations at our respective emails. Thank you for the presentation. Done. Fuck yeah.